Hello, everybody. This is going to be your lecture for the remainder of Chapter 4, which includes Newton's second law and friction. You're going to add annotations to handouts 34 and 35, which are friction and Newton's second law. Handouts will be glued into your notebook as those numbers. So this is the final lecture for Chapter 4. We've already covered mass and weight, free fall, non-free fall, and force causes acceleration. We will briefly review that now as part of this first section. All right. So force causes acceleration. Acceleration is directly proportional to net force. So when something is directly proportional, there's a couple ways of describing that. One is to say they're directly proportional. You can also say that they're equivalent, right? And basically what this means is if I increase net force, okay, if I increase net force, then acceleration increases as well. That's all that means. And then the opposite's also true. So that means acceleration and force go the same direction as each other. So if force decreases, it decreases the acceleration. So basically, if you push it harder, it accelerates more. If you push it less, it accelerates less. So kind of it's pretty straightforward and intuitive. So that is the main thrust of Newton's second law: force equals mass times acceleration. If you apply a force to a mass, a net force to a mass, it will accelerate. And next slide, the force of friction. Friction between two objects depends on the types of materials that they are. Imagine rubbing your hand against your hand. There's a certain amount of friction there, types of materials. If you were to take your hand and rub it against something rough like asphalt or something, there would be a different amount of friction there. And the friction itself is just due to surface bumpiness. So if you have 100% no bumps, then you have no friction. And in most cases, we do have friction. You can have friction in any material. As long as there are two things, you will have friction. Different materials have different frictions. So if you can imagine rubbing your hand across a table versus across asphalt, it's going to be different. And this is just due to like microscopic differences and stickiness, which is just the attraction of the atoms to each other. And it says friction between a crate and a smooth floor is less than if the floor is rough. So it's like trying to push a couch across linoleum or wood floors versus carpet or thick carpet. The rougher the surface, the greater the friction, which is the greater the resistance. So when you move through air, there's a certain amount of friction. But if you're moving through water, there's a different amount of friction. So it's a lot easier to run through air than it is to run through water due to the density of the liquid. So air is a much less dense versus water. So, and then if water was replaced with something even thicker, like honey, it would be even harder to move through that. This image here is just taking two books and it's looking at them at a microscopic level. And so this is interactive, so you're welcome to actually use the simulation yourself. So what we see here is we have two different surfaces and the little circles represent the atoms. When I move the chemistry book against the physics book, it causes the temperature to rise. Notice the thermometer is increasing and the movement of the molecules is increasing. This is due to friction. So the energy that is being put into the motion of the two books is partially being transferred into heat. So it's becoming heat and escaping. And this is really the role of friction in general. So in any system, when we lose energy, it's mostly due to friction. So a internal combustion engine is, I forget the percentage efficiency, but it's not very high. Most of the energy that is used by an engine is released as heat. That's why cars, like if you driving your car and your hand on the hood, it's hot. Most of the energy is actually lost as heat, just due to the movement of the parts against each other. It is not efficient. And so, and that comes from friction. And that is where we lose energy all the time. So in experiments in the lab, we'll not get an exact number because we're not calculating in heat loss by friction. All right, the first question, the force of friction can occur with sliding objects, in water, in air, or all of the above. So to have friction, you just have to have two things moving against each other. And sliding objects, yes. In water, in air, both are definitely places that friction can occur. And here's an additional little expansion of that idea. Friction can also occur in objects at rest. So the reason why when you start pushing something heavy and it doesn't move right away is because of friction. So friction is essentially canceling out your applied force, which is why the object doesn't move immediately. You have to break a threshold of friction before your object will start to move. So if you push with 10 newtons of force on something, it may not move until you get to 50 newtons of force, at which point it would start moving. So you're applying a force all the way up to 50 newtons, and then all of a sudden you've kind of broke that friction and it starts to move. You've exceeded the amount of friction between the object and the surface. The next two questions are about pushing a refrigerator. When Sanjay pushes a refrigerator across the kitchen floor at constant speed, the force of friction between the refrigerator and the floor is. So the key to understanding this is actually in the constant speed. In Newton's second law, F equals ma, when constant speed tells me that one of these variables is zero, just right off the bat. So if constant speed means I'm not changing velocity, which means that I do not have acceleration. So acceleration is zero. So the mass, regardless of what it is, times zero means that the net force is also zero. So it says when he pushes the refrigerator at a constant speed, the force of friction between the refrigerator and the floor is what? So we have a net force of zero whenever our forces all cancel out. So he's pushing the refrigerator to the right, which means that the friction is acting to the left. So this is his push, and then this is friction. Okay. And so for force to be zero and acceleration to be zero, then these two have to be equal and opposite. So the answer would have to be that the friction is equal and opposite to Sanjay's push. It can't just be equal, because if it's the same way, it would have added to it. So it's opposite. So the correct answer would be C. Next question. When Sanjay pushes the refrigerator across the kitchen floor at an increasing speed, the amount of friction between the refrigerator and the floor is what? So in this case, we do have some acceleration. So if we have an increasing speed, we have acceleration. It is not zero. So it is not zero, it is some number, which means that the net force is also some number. It's not zero. This means that if it is increasing to the right, then his push must be larger than the friction. Okay, so for there to be extra force to increase the speed, then that means that there is more push force than there is friction force. So the correct answer would have to be A, less than Sanjay's push. All right. Mass resists acceleration. So we are talking about the relationship between force and acceleration when mass is constant and it's directly related. So more force equals more acceleration, less force equals less acceleration. We also want to look at the relationship between mass and acceleration when force is constant. So the trick to kind of predicting what will happen in these equations is to make one variable constant. So you can't have all three changing and make a prediction. You have to have only one thing changing and one thing responding. So in this particular case, for mass resist acceleration, we're going to have force be constant, which means it's not going to change. It's going to stay the same. The only thing we're going to change is either mass or acceleration with the same amount of force. So if I happen to increase the mass, it will actually decrease the acceleration. And the opposite's also true. If I decrease the mass, I increase the acceleration. An example of this would be if you are on your skateboard going down the sidewalk and you pick up a backpack as you're rolling. If you are not adding any energy to your movement, you will slow down. So if you also do the opposite, which is if you're rolling along the sidewalk and then you drop your backpack, you will go slightly faster. Now, there's a lot of factors involved there. Obviously, there's the friction of the sidewalk and there's all of those things in motion. But you can kind of get the idea that if all of a sudden your mass became a lot greater, it would affect your velocity in the opposite way. So another example would be if you were running and then all of a sudden someone jumped on your back. It would be, you would definitely slow down and not be able to run as fast that way. And then, of course, the opposite being true. So it is an inverse relationship, meaning that if one increases, the other decreases. So they're opposites if force is constant. And we call this inversely proportional. So Newton's second law essentially wraps all of those things up together. So it includes force, mass, and acceleration. And we see that acceleration is produced when there's a net force on an object, which is directly proportional. So more force means more acceleration and is inversely proportional to the mass. So if the mass increases, the acceleration decreases. Those are opposites. In equation form, so the variable for acceleration is a lowercase a, net force is a capital F, and often they'll use subnet to indicate that that is the net force. There's a lot of different forces, and so using subscripts helps distinguish these. So you have force due to gravity, you have normal force, you have weight force, you have net force, you have force in the x direction, force in the y direction, et cetera, et cetera. So by using subscripts, it helps you identify which force it is that we're talking about. So net force, and then mass is lowercase m. And it's typically written as F equals m times a. That is the typical way of writing that equation. It depends on what you're solving for, of how you would adjust this equation, but the overall equation is usually written this way, F equals m times a. Being down. Okay. Second law of motion. This image shares a couple different relationships between force, mass, and acceleration. The first would be this top two here. So if you apply an equal force to a brick here, force of hand accelerates brick, force of hand accelerates brick. If you apply the same force, so this is force is constant, and you double the mass, then that would be increasing m. So if we're using a constant F, that means increasing m, which is mass, would decrease acceleration because those two are opposites. If we further increase mass, we further decrease acceleration. So this is showing if I go with the same amount of force and I go 1 brick, 2 bricks, 3 bricks, my acceleration goes to a half and then to a third. If I change the amount of force but leave the mass the same, so this would be force equals mass, but mass is constant this time. So this is constant. Then we are looking at the relationship between force and acceleration. So if I double my force, then I double my acceleration because force and acceleration are directly proportional, meaning if one increases, the other increases. For mass and acceleration, they're opposites. One increases, the other decreases. Then if I double the force and I double the acceleration, it actually doesn't, or I'm sorry, if I double the force and the mass, it doesn't change the acceleration. And that's just, I mean, if you plug in the numbers is what is probably the best way to view that. But if I were to say that I'm applying 1 Newton of force to 1 kilogram at 1 meter per second squared, okay, and then I say I'm going to double the force, okay, and double the mass. So force will become 2, mass will become 2, and we're going to solve for acceleration. To solve for acceleration, I have to divide both sides by 2, which gives me 1 equals acceleration. So if I double both the force and the mass, acceleration will actually stay the same. All right, first practice question. Consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half, what happens to the acceleration of the cart? So we start off with force equals mass times acceleration. And I'm just going to plug in 1 for mass and force. And that would give me an acceleration of 1. This would be like my starting values. Then I'm going to do the change. It says if the force remains the same. So force is still going to be 1. And it says while the mass is decreased to half, so half, what happens to the acceleration? And so to solve for A, I would have to multiply both sides by 2, which would give me 2 equals A. And so A goes from 1 to 2, meaning that it indeed doubles. Last question. Push a cart along a track so twice as much force acts on it. If the acceleration remains the same, what is a reasonable explanation? All right. So we're going to, all right, last question. Push a cart along a track so twice as much net force acts on it. If the acceleration remains the same, what is a reasonable explanation? All right, so I wrote our formula, F equals M times A. I plugged in ones for everything. So net force of 1 equals mass of 1 times acceleration of 1. And it says if the force is doubled, so I doubled the force, and it says if the acceleration remains the same, so I put it as a 1, what is a reasonable explanation? So looking at the math here, the only way the second equation is correct is if mass doubled and became 2. So let's look at the choices. The mass of the cart doubled when the force doubled. The cart experienced a force that it didn't before. The track is not level. Friction reverse direction. The last one isn't possible. And the B and C are nearly impossible to really determine. But we do know mathematically that if the force doubled but the acceleration did not change, the only explanation would be that the mass increased. So the mass would have to actually technically double for this equation to work out correctly. So the correct answer would have to be A, the mass of the cart doubled when the force doubled. All right, this is the end of the lecture. Make sure you have attached 34 and 35 into your notebook and added annotations. They will be stamped next week. Thank you.